Hi everyone, I'm Shreyas and I want to introduce you to our paper, Point Processes for Competing Observations with Recurrent Networks, or Popcorn, a generative model for EHR data. To start, I want to show some key properties of EHR data. Here we have some fake data across 3 different features collected during a patient's stay: blood pressure, hemoglobin, and diuretic administration. The main properties to note are that 1, features are sampled at very different frequencies. 2, the past history can affect what and when future observations occur. So in this case, diuretic administration affects how often BP and hemoglobin are sampled and when they're observed. And finally, observations and times are correlated. When something is observed changes the likelihood of what that observation will be. Given these properties, EHR data can actually be modeled very well using the framework of a multivariate point process, or MPP. An MPP is a random process which models sequences of events and event types. The basic idea is to model the likelihood of the next event type and time given past history by reasoning over each individual event density. We can use our initial example to sketch how an MPP works. First, we observe some data point for BP, and then we have 3 distributions for the probability until the next event. These 3 distributions are pitted against each other in a race to see which one will be the next observed and when the observation will happen. In this case, a blood test is ordered next and hemoglobin is reported. This process continues with each distribution updating to incorporate the newly observed data until we reach the end of the time series. It should be noted that typical MPP models use the intensity function rather than the probability distribution for modeling purposes. Our model, the popcorn model, uses a slightly different objective and models the probability densities directly, as shown in the example. There are roughly 2 parts of the model. The first part provides an embedding of all past observations up until the present, as shown in the large blue box on the left. This hidden vector is then transformed via neural networks to parameterize the event distribution. Subsequently, we develop an objective which specifies the joint likelihood of the next event and time given these distributions. The main advantages of our approach are that it has a closed form likelihood, making optimization straightforward. It directly encodes the dependence between the times and events. It has flexible parameterizations for the event likelihoods, and finally, it allows for direct forward sampling. Our objective does assume conditional independence of the event distributions given history, but we show empirically and theoretically why this restriction does not hinder model performance. We tested our model on 4 datasets commonly used in the point process community, including 3 EHR-based datasets involving mimic and Cynthia synthetic EHR data. For the EHR datasets, our model matched or outperformed on next event prediction measured with F1 or URC. We also matched the performance in comparable approaches for lag likelihood. If you want to learn more, check out our paper and come by our poster. Thank you.